So then another person was also studying bacteria, and this was a complete accident, this one. He wasn't looking for any drugs or anything. He was just growing bacteria. And he was lazy. He left a petri dish out on the bench that had bacteria on it. And he went away for a few days. And he came back, and some mold had gotten on his petri dish. And you know that blue mold you get on your bread? All right, the blue mold on your bread. All right, well, that's penicillium most of the time. Don't eat it, though. All right? But, all right, so so the blue mold, I should have gotten a picture of this and thrown it up there too. The blue mold had a halo around it where it killed all the bacteria. And he thought, well, that's kind of interesting. So he started working on it, and he didn't actually identify it, but this was the active compound in that mold that the mold was releasing. This is penicillin right here, all right? And so some other people came along, Howard Florey and Ernest Chain, and penicillin is really hard to work on chemically. It's a very unstable molecule. It's a hair trigger kind of a molecule, all right? It's reasonably stable, but if you add some acid to it, it falls apart. If you add some base to it, it falls apart. If you heat it up, it falls apart. If you look at it sideways, it falls apart, all right? So it was hard to isolate, and it took all the way to World War II to really get this into commercial production. But this then, this was such a good antibiotic that it really kind of displaced the sulfonylamides. The sulfonylamides were on this nice track. Then along came penicillin. It's even better. So then the sulfonylamides kind of fell by the wayside for like 60 or 70 years until all the bacteria became resistant to the penicillins, and the sulfonylamides are now kind of back. So next slide. So what's happened since this early days is the sulfonilamide, sulvarsen was developed back here, but it's an organoarsenical. It's really toxic, all right? So arsenic is everyone knows, don't eat arsenic, right? You all know that? Okay, don't eat arsenic, all right? But these drugs have arsenic. The same thing with mercury. Don't take mercury, all right? So the sulfonylamides are here, and then here comes penicillin. Now, this top part here is when a drug was introduced, and the bottom part here is when the resistance showed up to that drug, all right? So here's the sulfonylamides, and resistance shows up, all right, within about 10 years. The penicillins, it didn't take very long either. But then the streptomycin came along, an aminoglycoside class of antibiotics, and some resistance shows up here. Here's chloramphenicol, resistance. Tetracycline, resistance. Erythromycin, took a real long time, but there's resistance. Vancomycin, one of my favorite drugs to study, took a really long time as well. Methicillin, a year later. I don't even think it was a whole year. I think it was 9 months. Anyhow, and I shouldn't laugh about that because now, so the cephalosporins were developed, and then the cephalosporin resistance occurred during the development of the cephalosporins, but they're still really fantastic, all right? And then the linezolid and daptomycin have been developed in the last period of time because there's like this gap here, and then there's this little blip, and now there's nothing, all right, again. And so this is the problem, is that we had this heyday of antibiotic discovery, and now we're in we're getting to what people are referring to as the post-antibiotic era, where we might not have anything left because of resistance to all these different antibiotics, all right? Now, some of these antibiotics have been developed using the chemical synthesis approach, but not very many. I think linezolid, and on this whole list, linezolid is the only one that was developed, and the sulfonamides are the only two that were developed through a hardcore medicinal chemistry approach. All the rest of these are natural products, all right? So like quinine is a natural product, right? All right, so it's isolated from nature, and most of our antibiotics are from nature. All right, next slide. So here's structures of a whole bunch of antibiotics, all right? And so here's phosphomycin, a nice simple one, all right? Here's cycloserine, another nice simple one. Both of these were identified from nature. Here's tetracycline, identified from nature. Cephalosporins related to the penicillins from nature. Vancomycin, one of my favorites, from nature. Linezolid is a synthetic drug. Colistin is a cyclic peptide from nature. And ciprofloxacin, which wasn't on that previous slide, is a synthetic drug. All right, so that's really kind of an overview of all these different kind of drug classes. So next slide. So some of these drugs act on bacterial cell wall biosynthesis. Penicillins act on bacterial cell wall biosynthesis. Cycloserine, phosphomycin, vancomycin, all act on bacterial cell wall biosynthesis. And this is the pathway that we focus on for our research, all right? And this pathway looks kind of scary. You know, if you're not used to seeing biochemical pathways, then this is a biochemical pathway. It's got a lot of steps in it, all right? The molecules are fairly complicated. This is uridine N-acetyl muramic acid. All right, this is like the core structure for this carrier that carries everything through the cell wall pathway. And there's an alanine branch here, which is L-alanine, an amino acid found usually in proteins. It's converted to D-alanine, and then it's converted to D-ala-D-ala, two D-alanines linked together. And then you have this whole pathway. You take UDP N-acetylglucosamine, convert it to UDP N-acetyl muramic acid, that molecule right there. And then you add an amino acid, another amino acid, and then these two D-alanines. Then you have to flip that, then that's transported into the membrane. It's another sugar is added from UDP NAG is added to make this. And this C55 is a 55 carbon carrier, a big giant lipophilic carrier. All right, it's like I don't even know a good analogy right offhand. To make lipid 2, this is flipped to the outside layer of the bacterial membrane, and then it's further elaborated, and then finally these things called penicillin binding proteins cross-link the peptide part. All right, so it's a pretty good sized pathway. All right, and this is how bacteria make their cell walls, and that's what makes them resistant, you know, like entities really, and all these different antibiotics act at different steps. So the beta-lactams all act here. So penicillins and cephalosporins are beta-lactams. They all act at this last step. Vancomycin, one of my favorites, binds D-ala-D-ala. And it sequesters the D-ala-D-ala right here so that this is stuck here. And that's how it kills the bacteria. Phosphomycin that I had on that one slide inhibits this enzyme right here. Cycloserine inhibits this enzyme, bacitracin inhibits this enzyme. So there's all these sites are targets for antibacterial agents. Next slide. And the penicillin binding proteins catalyze a reaction where they attack the D-ala-D-ala to form an enzyme adduct. And then they transfer this acyl group from the serine either to water or to an adjacent strand to form a cross-link. And that cross-link is important for cell wall strength. All right, so next slide. And let's go to the next slide. So this is transition state theory. So if you want to inhibit an enzyme, Linus Pauling figured this out. Linus Pauling's a very smart guy. He got 2 Nobel Prizes, so that means he's smart, right? So if you get 2, you're smart. All right, if you get 1, you're smart, but if you get 2, you're like twice as smart, or even more. But one was a Nobel Peace Prize, so I don't know if we can count that or not. But anyhow, okay. So an enzyme catalyzed reaction takes a substrate to a product. So this is the uncatalyzed reaction here. And there's this energy barrier, and it's huge, right? I mean, it's like climbing over Mount Everest to go get a drink of water or something is what it is, all right? So what an enzyme has to do is it has to lower that transition state energy, all right, in order to catalyze this reaction, to make this faster. And so what the enzyme is doing is it's pulling down this, it binds to the substrate, but what it does is it binds to the transition state much more tightly, all right? And if you look at the energy profile, it looks like the energy profile for the enzyme is perfectly matched to pull that transition state down in energy by binding it as tightly as it possibly can. It's driving the reaction by binding to the transition state, all right? And this is like basic chemical reaction theory, all tied up with proteins and enzymes. Next slide. And the penicillin binding proteins attack this. This is that peptide bond here. Let's go back one slide, sorry. So how profound do enzymes catalyze reactions? If you look at an uncatalyzed hydrolysis of a peptide bond, the half-life is estimated to be about 50,000 years, all right? But now when you eat steak, it doesn't take you 50,000 years to digest that steak, all right? Because you have enzymes in your stomach that catalyze the hydrolysis of the steak. So in the presence of the enzymes, the steak dissolves on it with a half-life of about 100 per second. Okay, this is very fast. 1 in 50,000 versus 100 is a really big difference, and that's a huge rate acceleration. So if you go to the next slide, and so the penicillin binding proteins go through this high energy intermediate to this intermediate to this high energy intermediate, then to this intermediate. And so the reaction profile for a hydrolytic enzyme looks like this, and the penicillin binding proteins have this kind of a profile. So the next slide. So what we did in our research is we thought, well, we're going to make some new inhibitors for the penicillin binding proteins, and we're going to use transition state analog theory to do it. And so what we did is we made things that look like the peptide in the bacterial cell wall biosynthesis pathway, but we stuck something called boroalanine on them rather than regular alanine. And boroalanine, it looks like regular alanine, but rather than having a carboxylate group, it's got this boron atom in it. And boron, you use it in the eye drops, right? If you ever look at your eye drops, you'll see boric acid in there. And it's this really nice buffer. And it goes from being trigonal to tetrahedral, and it's got a nice pH for that, around pH 8.5, all right? But if you look at the reaction catalyzed by the penicillin binding proteins, it goes through a tetrahedral intermediate too, and it's really high in energy, all right? And it's almost, it's very hard to generate. And a boron atom does it really easily. And so what happens is if you make the right analog of a cell wall with boron here, the penicillin binding protein is going to grab onto it, and it's going to think, I'm going to lower the energy of that thing, and it's going to fall, it's going to react with it, and it's like falling into a bottomless pit almost. It's going to grab onto it, and it's going to be stuck there, and it won't be able to get off, and you've got an inhibitor. So go to the next slide. And we actually stay here for a second. So we actually made this inhibitor, and we got crystal structures of it with the collaborator. And we can see it's perfectly tetrahedral, bound to that active site serine. We can see exactly what's going on. Actually, this tells us almost perfectly what the reaction mechanism for this enzyme was, because we can see all the hydrogen bonding network. We can see everything that's going on. So from a basic science point of view, it's like the ideal inhibitor. If you want to know how an enzyme works, you make this kind of an inhibitor, and you get a snapshot of the reaction intermediate. Okay, so go to the next slide. So we